All right, we're going to look at this problem that I started on the board today. Y equals 3x cubed plus 2x squared, and we're going to find the local extrema, right? The local maxes and mins, the relative extrema, local max and mins, all the same thing. So the way you find local extrema can occur where the first derivative is 0 or undefined. So we have to take the first derivative of this. Pretty simple one. You get 9x squared plus 4x. Set that equal to 0. Notice there's no place that 9x squared plus 4x is undefined, so we don't have to worry about kinks in the original equation. But 9x squared plus 4x is set equal to 0. If you factor out the x, you get 9x plus 4. So this is a zero factor property. This is 0 when x is 0 or when 9x plus 4 is 0. And if we solve that for x, you get 9x equals negative 4. Divide both sides by 9, you get x equals negative 4/9. So these are called critical points. These are places that local extrema can occur, which means it's also places where absolute extrema could occur. We'll talk about that in a second. So if you put 0 in the original equation, you get 0. And if you put negative 4/9 in the original equation, you get 3 times negative 4/9 cubed plus 2 times negative 4/9 squared. And negative 4 cubed is negative 64. 9 cubed is 9 times 9 is 81. 9 more times 9 more is 729. Plus 2 times negative 4/9 squared is a positive 16 over 81. We need the same denominator here, so I have to multiply this by a 9 over 9 to get 729 on the bottom. So this equals 3 times negative 64, which is negative 192. And then this top here, 2 times 16 is 32, and 32 times 9 is 288. So this is plus 288 all over that common denominator, 729. So you get 288 minus 192, which is 96, positive 96, all over 729. Notice if you add the digits of 9 and 6, you get 15. Add 7, 2, and 9, and you get 18. 15 and 18 are both divisible by 3, which means the original numbers are both divisible by 3. So 3 goes into 96 32 times, and 3 goes into 729 243 times. All right. So at the points 0, 0, remember I put a 0 and I got a 0 out, and at the points negative 4/9, 32 over 243, these are candidates for local extrema. We just need to know, is it a relative max or is it a relative min? All right, relative max or relative min. I'm going to teach you the second derivative test to do this. Now remember, I talked about concavity in class. So wherever the second derivative is positive, the original function is a smile. So the second derivative could be positive here, and I'm still part of this smile. It could be positive here, I'm still part of this smile. It could be positive here, I'm still part of this smile. When the second derivative is negative, the original function is frowning. All right. The moment I change from a smile to a frown is called an inflection point. So here I'm concave up, second derivative is positive, second derivative is positive. So right here, the second derivative would be 0, and then second derivative would turn negative because I'm frowning. Second derivative negative, 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 negative. If this kept going, right here is where I changed from this frown to a smile again. This would be another inflection point. Second derivative would be 0 there. But I just want to see the sign of the second derivative. So if I take the second derivative, remember right above y prime was 9x squared plus 4x. We already did that. So y prime prime, the second derivative, is just the derivative of the first derivative. So I get 18x plus 4. And I'm going to evaluate that when x is 0 and when x is negative 4/9. When x is 0, y prime prime of 0 equals 18 times 0 plus 4, which is 4. And I don't care about the number 4, I just care about the fact that 4 is positive. So that means that this position, 0, 0, is on the bottom of a valley, because the original function looks like this at the value 0, 0. At the value 0, 0, I'm part of a smile. How do I know that? Well, because the second derivative of 0 is positive, and positive is a smiley part of a function. But I know I'm on the exact bottom part of the smile. How do I know that? Because when I put 0 into my first derivative, I get a 0 out. When I put a 0 in for 9x squared plus 4x, I get a 0 out, which means the slope at that function must be flat. So I'm at the bottom part of this smile because the slope of that function must be flat there. I know I'm on a concave up portion of my function, but I'm on the flattest part of that concave up portion, which means 0, 0 is a relative min. Okay. Now, the AP Calculus is very particular about this, how you answer this question. You could say the relative min occurs at x equal to 0, and the value of the relative min is f of x equals 0 in this case. Relative min occurs at x equals 0, and the value of the relative min in this case also happens to be 0, but it's f of x equals 0. Okay? Negative 4/9 is where we're going to check our second derivative again. So again, recall that the second derivative is 18x plus 4. So we're doing y prime prime of negative 4/9. That is 18 times negative 4/9 plus 4. 9 goes into 18 2 times. 2 times negative 4 is negative 8, and negative 8 plus 4 is negative 4. All right, so this, when I put negative 4 in and get this 32 over 243 out, that's at a concave down portion. Because my second derivative is negative, I'm at a frowny portion of a function, but it's at the slope equal to 0 portion of that frowny portion, because when I put negative 4/9 into my first derivative, I get a 0 out. So the slope at negative 4/9, 32 over 243, must be 0. And since I know the second derivative is negative, it's at a concave down portion. So I know that the relative max occurs at x equal negative 4/9 with a value of 32 over 243. All right. So f of negative 4/9 is the value of the relative max. Negative 4/9 is the value of x that gets me my relative max. So you could say the relative max occurs when x equals negative 4/9, but the value of the relative max is 32 over 243. Make that distinction, because they'll count you wrong every time on the AP test. If you say the relative max is negative 4/9, you're wrong. Relative max is 32 over 243. It just occurs when x equals negative 4/9. Okay? And if we look at this graph on Desmos, 3x cubed plus 2x squared, let's look at it real quick. Y equals 3x cubed plus 2x squared. You get this function. Let me blow it up. And notice the relative min does occur at 0, 0, and the relative max occurs up here at negative 0.444, 0.1317. All right, and if we did some math here, let me just go back and look. Negative 4/9 and 32 over 243. So negative 4/9 is your negative 0.444, and your what was it again? 32 over 243 over 243 is your 0.3168, and that's this point right here. That's your relative max. So negative 0.444, comma 0.1317, it rounded up. But that's fine. That's my relative max. Okay? That's how you find local extrema. Relative mins, relative maxes. And it also gives you a good shape. I already knew this was a cubic function, so it has this particular shape. I knew it went through 0, 0 because that's easy to see in the function. If I put a 0 in, I get a 0 out. Don't really know this one yet, but I can set the original function equal to 0 to find this other point where it crosses the x-axis, this other 0. But I can find relative maxes and relative mins to get the rest, the other shape of my function. It's really good for function graphing if you have to do it on your own. Okay. All right, that's it for relative extrema. And again, notice that my function was concave down at this negative 4/9. When x was negative 4/9, I am in a concave down portion of my function. And the second derivative was negative at negative 4/9. And then when I put a 0 into my second derivative, it was positive. And the point 0, 0 is part of a smiley section of my original function. Okay? So that is relative extrema in a nutshell. There's also a first derivative test. Let me see, I have 3.5 minutes left on this video. Now we'll just cover the first derivative in class tomorrow, but make sure you understand this. Take the original function, take the derivative, set the derivative equal to 0, and wherever the first derivative is 0 or where the first derivative is undefined, those are candidates. Those are called critical points. They're candidates for local extrema. And then you got to see if they are local extrema. They're also candidates for global extrema, and we'll get into that tomorrow as well. So we're going to look at global extrema tomorrow, and we're going to look at how you use a first derivative test to find out if it's a max or a min. Okay? All right, that's all I have.